Hi everyone. I'm really sorry not being able to attend physically. I'm Sergei, and today I'm presenting our joint work with Amin on solving guarded domain equations in Presheaves over Ordinals and mechanizing it in a ROC proof assistant. So firstly, I'm going to go briefly over our motivation for this work. And next, I'm going to switch what was the gap that we tried to close and what are our results. Firstly, about the context. Often when reasoning about programming languages, we are interested to study programming languages that have fixed point combinators. So for example, on this slide, you can see programming language that employs a fixed point combinator. And the intended classical operational semantical rule for it is that if we apply it to a value, then we substitute this value instead of the variable, and we substitute the function itself instead of its bound name in the body. And when we study languages like this, we're interested in not just studying operational semantics, but also in objects that can represent this language. So a classical problem from the notational semantics is how to find a suitable object where we can interpret our language in a way that operational rules become either just equalities in this mathematical object or equalities modular some simple constructions. And one of the approaches to do it is to try to solve the recursive domain equation, which is a really old problem. So in this particular case, for this subset of the language that we see on the slide, we need an equation that at least includes a function space to interpret fixed points, and probably some other gadgets depending on what else we have in the language. And already out here, you can see that in classical math, in classical mathematical world, there would be a problem because we have a negative occurrence of d in the function space, and obviously we have size issues. I mean, if t does not make it trivial. So one of the approaches to deal with such recursive domain equations is to use guarded theorem. So in this case, instead of t, we are going to use later modality, and the theory behind it is going to help us to make well-formed definitions. And if you are not familiar with guarded theory, the intuition behind it is that instead of consider D to be a set, you consider it as a set in the context of some fuel, and whenever we step under a later modality, we consume a unit of fuel. If we are out of fuel, then it becomes a trivial set. So if we look and an important note, when we represent languages like this, usually for technical reasons, it's beneficial to have one more construction out here. And now if we look at those sets with different amount of fuel, we can see how it unfolds, and that it should be it should convince you that it's well-founded, because on the stage 0 we do not have anything interesting, and on all the subsequent stages we depend on something that was previously defined. Okay. Now in this setup we already have this setup already provides us with all the gadgets that allow us to reason about such languages. So later is supposed to be a pointed applicative on the functor, which allows us to actually do computations with functions here. And moreover, it has a fixed point combinator that allows to define semantics of fixed point constructions. So for example, if we want to interpret this subset of the language, then we consider it with some environment. In the variable case, we do a lookup. And in the fixed point case, we use the fixed point combinator of our interface, take function at the next step, and inject it into the environment together with a normal function argument. And now if we, for example, consider application of fix f x e to some value v, then by fixed point rule we can push the function outside, and by applicative structure of later we can push the argument inside and do the expected application. So in a nutshell, to reason about languages like this, we need later with those properties, ability to solve recursive domain equations, and moreover to have eternal fixed point combinator. And there are multiple setups that provide such interface. So for example, one really popular one is the one employed by Iris, where deep inside Iris they use certain formalism called ordered families of equivalences. And intuitively, it's just a type with step indexed downwards closed family of equalities. And you can also make it complete by providing an operation that computes limits of chains and saying that those limits should agree up to certain equality with the value in the chain. And it works really well for natural number case. So when we do our indexing over natural numbers, and in this case, you get a solution procedure for a certain subset of functors that allow to solve multiple of equations. So for example, the one for D can be solved using this domain equation solver. The one used in the core of Aris for iprop can be solved with it. And the advantages of this approach is that it is implemented in a host proof assistant, so we can rely on other machinery provided by the proof assistant. So for example, if you want to do some probabilistic programming, you can use something from MathComp. And moreover, since it's implemented on top of existing proof assistant with more or less clear semantics, it is easier to extract something that is deemed to be an understandable proposition. So, for example, in Iris, you can prove something using Iris proof mode, and if it's pure proposition, you can extract it back into the ROC world. Now I'm going to go over the gap that we try to cover in this work. So in certain cases, we want to go beyond indexing over just natural numbers. So for example, if we would like to study applicative biosimulation for the type that I provided before on the slides, then we would need to use something called an existential property. And the idea is if we consider it to be a statement in the language of Coffice, then if we unfold everything out here, then we would have some implicit quantification over step indices before the validity judgment. So in a way, we require that exist and for all compute for certain cases, which is not true if we do indexing over natural numbers. But if we but in some cases, if we consider regular ordinals, we can do this commutation. So for example, if instead of natural numbers we would use the first uncountable ordinal, then we could use this existential property. There is existing work that implements it also in Iris. And it works nice for certain use cases, but not for all of them. And the reason for it is that the recursive domain equation solver is a bit different. So note that coffee is a subset of offie, and since we require it in the argument keys, essentially what we ask for is that given some offie, we can complete it with our functor. And for example, the functor for D does not have this property, at least not in the setup of office and coffees. So for certain cases, this works. So transfinitaries can be used to implement iprop in the context of high ordinals, but not this type, for example. And the gap that we were trying to close in this work is to solve domain equations of this form over high ordinals, with the hope that in future we will use it for applicative bisimulation for types like this. There is another line of work that was covering same problems, namely first steps in synthetic guarded domain theory, where instead of office and coffees, the authors considered to work with sheaves and presheaves over ordinals. So in the original work, it was done with sheaves, and it works really nice on paper. But if we want to formalize it in a proof assistant, we would like to get rid of most of the complexities, and working with sheaves in a proof assistant is a relatively big complexity. So instead, we looked at the paper and tried to see if it's possible to simplify it and distill what sheaf properties we need and where we need them to work only with presheaves without maintaining sheaf condition for everything we construct out there. And our solution is to implement everything with presheaves and try to do it in Rock Proof Assistant, preferably with no admits. And a small spoiler, that was a success. And now I'm going to briefly go over the details of this work and describe intuition behind it. So for in the context of this work, I'm going to talk only about presheaves and sheaves over ordinals. So sheaf condition is going to be simplified. So as a quick reminder, presheaves in this case can be considered to be just step index family of sets with certain restriction functions, and the only difference with sheaves over presheaves when we consider them over ordinals is that for limit ordinals we have an additional condition that sheaf at a limit ordinal is supposed to be isomorphic to a limit of sets.
Around 5 minutes left for the talk. Would you mind to wrap up so there's some time for questions as well?
Yep. Yeah. Of stages below it. And if we look at the definition of later, we can see that it does exactly transform any presheaf into a sheaf. And moreover, the only time we need to use sheaf condition to construct fixed points is when it's under later. So that made us, so for example, in case of contractive functions, we require that the contractive function can have, all contractive functions can have fixed point and contractivity embeds later by using next. So we always work with sheaves by the properties of later. So we can just prove properties only of later and work with presheaves in the rest of the formalization. And that already gives, so I'm going to skip over it, that already gives us eternal fixed points. And now I'm briefly going to describe how recursive domain equations work. So the original proof relies on the fact that the presheaves are self-enriched, so every home set can be represented by an exponential. And recursive domain equation solver works for entafunctors that are locally contractive in a sense that they the corresponding enrichment functor action is contractive on home sets. And the proof is almost the same as in the original work, except for a different tower construction. And the reason for it is that we need to since we do not work with sheaves but with presheaves instead, we need to do their actions that allows us to make the distance smaller on every stage, and in particular on the limit stages. So with those three insights, we were able to formalize it, and on the slide you can see a small example of what we can do. So that's the original functor for D that was shown in the very beginning. We can really quickly show that it's locally contractive and obtain a solution for it. And the big, rather like distant view on this work is that left side of this diagram is something that works really nice in a proof assistant, mostly because office and office are sets with certain properties, and we can reuse a lot of host proof assistant machinery to reason about it. And the right side is a bit theoretically better, but working with sheaves is complicated in a proof assistant. So we try to push the complexity by working with pre-sheaves. And we implemented eternal fixed point, recursive domain equation solver, and eternal logic. And we assumed on the axiom of choice propositional extensionality and functional extensionality. And as a bonus, I think I do not have time. Thank you for your attention.